Good morning. In today's lesson, we are going to basically talk about what calculus is and then begin to look at the concept of a limit, both numerically and graphically. There's basically four ways we want to represent every single problem in calculus. We want to look at every single problem or concept numerically, graphically, analytically, and verbally. So today we're going to look at the numeric and graphical part as well as the verbal part. These first two pages are basically just a pictorial representation of what calculus is. So this first one on the left is without calculus, on the right is with calculus. So you guys we all know how to find the value of a function at a specific x coordinate. We just plug x into the function and it'll give us the y, and that's the height of the graph or the value of the function. On the right, the limit as f of x as x approaches c. Sometimes we know that there's holes in the graph, therefore f of c does not exist. However, there's a concept of a limit that's fundamental, it's foundational in calculus. It's what all of calculus is built around. And that's what we're going to look at this entire first chapter. This entire first page is what we're going to look at the entire first semester as well. On the left, we can find the slope of the line just using simple algebra. On the right, the slope of a curve. So it's basically, just like below it, the slope of a tangent line to a curve. A concept we can understand, average rate of change. We could just use distance equals rate times time. But on the right-hand side, instantaneous rate of change. We know that when we drive, we're not going 30 miles an hour the entire time. Our speed varies, so calculus will allow us to find that speed. And then there's a couple of other examples you can look over. In the second semester, we're actually not dealing with the slope of a tangent line, but something that seems unrelated but is very related, area. On the left, we can find the area of a rectangle. It's just length times width. But on the right, the area underneath the curve. We can get a good estimate using geometry, but we can't get an accurate answer, but we can with calculus. And then you can look over the rest of the examples there. Okay. And then this is another page. I could probably take this out, but calculus boils down to two major problems. The tangent line problem, that's what we're going to discuss the entire first semester, and the area problem, which we're going to discuss the entire second semester. Let's see, on the bottom we do have two questions, calculus or pre-calculus. How far have you driven if you're driving at a constant 30 miles per hour for 2 hours? Well, that's just distance equals rate times time, so that would just be pre-calculus, or even just algebra. However, how far have you driven if your speed is continuously changing for 2 hours? That's a situation in which we'd need calculus to figure it out. Okay, so let's just get into the meat of things here. Finding limits graphically and numerically notes. Suppose you are asked to sketch the graph of the function below. You can do this by using curve sketching techniques or by plugging in values of x and getting values of y and plotting the ordered pairs. But what about when x equals 1? So if I take this function and I look at evaluating the function at 1, I have 1 cubed minus 1 over 1 minus 1, which is 0 over 0, which is something we call the indeterminate form. It's not 0, it's not necessarily anything, it's what we call the indeterminate form. So when something like this happens, this is what we're going to look at this entire first chapter, we want to calculate something called the limit. So what I did here was I took the liberty of plugging in several values of x that get closer and closer to 1, both from the smaller side of 1 and the larger side of 1. And I think you guys can see as we plug in values of x that get closer and closer to 1, the value of y gets closer and closer and closer to the number 3. So even though f of 1 does not equal 3, the limit as x approaches 1 of f of 1 is 3. So let me explain that with some notation down below. This is the concept of a limit. If f of x becomes arbitrarily close to a single number, L, as x approaches c from either side, so L is going to be your y, and c is essentially your x. The limit of f of x as x approaches c is L. And this is written as this expression here. So this, the limit of f of x as x approaches L, or I'm sorry, as x approaches c is L, is how you read that notation. Okay. So our first example, evaluate the function f of x equals, well, that function, at several points near 0 and use the result to estimate the value of the function near 0. So again, I took the liberty of plugging in values of x that are close to 0, approaching it from the negative and positive side, and I think we can all see that the value approaches 2. So how I would write this is the limit as x approaches 0 of f of x equals 2. And that's how we do it numerically. I'm going to ask you to do this once in practice. You're not going to have to do this all that much, but it does work with tables as well, kind of, and I'll show you that later on. All right, you can also find the limit of a function simply by looking at its graph. If the graph approaches the same y-coordinate as you travel towards your x value from both the left and the right, that's important, from both sides, it has to be the same, that y value is the limit of the function. So in this first example, blow this up a little bit, the limit as x approaches -2 of f of x. So here's -2. And as I'm approaching -2 from the left and from the right, my arrows are coming together, so they're both approaching the same number, and that number is the y-coordinate, -4. So the limit as x approaches -2 of f of x equals -4. My second example, it's almost the same picture, except here I do have a value of f at -2 defined. It's up here at, what is that? I guess -1. But that doesn't change the limit. In this problem, f of -2 is equal to -1. However, the limit as x approaches -2 of f of x is, as I approach x equals -2 from both sides, again, I'm approaching the y-coordinate, -4. So once again, the limit as x approaches -2 of f of x is -4, whether that value of x is defined or not. Okay. Couple crazy graphs here. So number 5, the limit as x approaches 1 of f of x. So as x approaches 1 from the left, it looks like I'm approaching, I don't know what that is, maybe -2. And as x approaches 1 from this other side, it's way up here. Since these two arrows do not come together, I guess that would be +2, since they don't approach the same number, we say that the limit of as x approaches 1 of f of x does not exist. This limit does not exist, DNE for short. So for a limit to exist, basically, if you were using your fingers to go along this graph from both sides towards one number, your fingers would have to come together. If they're separate, it does not exist. Number 6, another crazy graph. It's called an oscillation. The limit as f of x the limit of f of x as x approaches 1 is. Now I can't really tell what's going on here. It's all crazy. So I can't tell if it's up at 1, if it's at 0, if it's at -1. So again, if it's an oscillation, I say that the limit does not exist as x approaches 1. Couple more. Number 7. The limit as x approaches 0 of f of x is. So as x approaches 0, I'm going to come this way and I'm going to come that way, and it looks like my arrows are coming together, and they're both coming together at the value of -1. Number 8, the limit as x approaches 0 of f of x. Now, from this side, it looks like I go up towards infinity, and from this side, it looks like I go up towards infinity. So, the limit as x approaches 0 of f of x, you could say is infinity. However, infinity is not an actual answer. It's not a number. So we say does not exist. You could technically say infinity or does not exist, but you have to know that they mean the same thing. Okay, use the graph below to decide whether the value of the given quantity exists. If it does, find it. If not, explain why. So, number 9. Number 9 is just f of 1. So it's not the limit, it's just f of 1. F of 1 is an empty or hollow dot, so f of 1 does not exist. Let's see, f of -1. F of -1, over here at -1, oh, I have a little break in my graph, and I have two parts of my graph coming together, but not together, separate. So the empty dot means that is not a value of f of -1, but the solid dot is, so I would say that this is equal to 2. All right, going back, the limit as x approaches 1 of f of x. So as x approaches 1, these two arrow tips come together, and they're both coming together at the y-coordinate of 2. So the limit as x approaches 1 of f of x is 2. Number 12, the limit as x approaches -1 of f of x. Okay, I'm gonna erase this so we can see a little better. So as x approaches -1, this value is continually 1, and it looks like this value is approaching 2. So since these arrows do not come together, I would say that the limit as x approaches -1 of f of x does not exist. A couple more here. I'm gonna clean up my picture a little bit. The limit as x approaches -3. Okay, over here at -3. As I'm approaching -3, this value, or from the left-hand side, I approach a y value of +3, as do I do from the right-hand side. So I would say that even though f of -3 does not exist, the limit does, and that limit is 3. Let's see, I think the last one almost here. The limit as x approaches -2. So from this side, it looks like I'm approaching a y value of 1. From this side, it's a constant 1. So I would say the limit as x approaches -2 is 1. So it's a fairly simple idea, I do believe. However, it's fundamental to all of calculus. And I believe, oh, we have one more. Yep, last one. Sketch the graph of f. Then identify the values for which the limit as x approaches c of f of x exists. So I have two questions here. What's the limit as x approaches 2, and what's the limit as x approaches 4? And I think you can see the reason that they chose those two values are because those are basically the endpoints of my different intervals. So sketch a little generic graph here. I don't know how big I might have to make it. Let's see, x plus 6. So I'm going to go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, this top portion, as x is less than 2, it's x squared. So we know x squared is a parabola, vertex at the origin, over 2, up 1, 2, 3, 4. So as x is less than 2, it looks like it would just be this portion of my parabola. Some of those points. All right, middle portion, negative x plus 6 from and including, actually, hang on, made a little mistake here. This should be an open dot on the end. Oh, and I did negative 2. What am I doing? Let's go back. I don't know why I was thinking negative 2. It's positive 2. So, it looks like it's going to be that. All right, sorry about that. Negative x plus 6 from 2 to 4. So my y-intercept is 6, down 1, right 1, down 1, right 1, down 1, right 1. From 2 to 4, so I'll go one more, down 1, right 1. So it looks like my graph's going to look like this, and I have 2 solid points on the end. Nope, that last one, sorry again. It's a hollow dot there because this inequality is just less than. And then 3x minus 4 for x is greater than or equal to 4. And let's go green. So 3x minus 4. 1, 2, 3, 4. 1, 2, 3 over 1. 1, 2, 3 over 1. 1, 2, 3 over 1. Oh boy. So to figure out this last one, what is that? 3 times 4, so it's going to be up here at 8. And that's going to be looking like that. So the limit as x approaches 2 oh, you know what? I made another big mistake here. I apologize. This should be up at 2 comma 4. 1, 1, 2. Those are on top of each other. There we go. All right, sorry about that. There's a good graph. Maybe I should include a coordinate plane on here to make a better graph. So for number 15, the limit as x approaches 2. As x approaches 2, it looks like I'm approaching 4 from the left and 4 from the right, so I would say that this is a value of 4. However, the limit as x approaches 4 of f of x. As I'm approaching 4 from the left-hand side, it looks like I'm at a value of 2. And as I'm approaching 4 from the right-hand side, I believe we said that value was 8. So, since these two numbers are not same, or since my arrows do not come together, boom, 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 does not exist. Okay, that's the basics on limits, graphically and numerically. Thank you.